In this lesson, we're going to look at propositional formulas, the language that we will use for describing the forms or structures of propositions. Here are the words and symbols that we've used for each of the different connectives so far. Conjunction, disjunction, the conditional, the biconditional, and negation. We have used the ampersand, the vel, the horseshoe, the tribar, and the squiggly negation symbol, the squiggly minus symbol, as ways of symbolizing these kinds of connectives. Well, we're going to use these as the basis of a precisely defined formal language, a language for describing form. Now, this language is made up of formulas, and we'll define the formulas of the language in this precise way. We start off with a collection of atoms. These are things that can't be broken up into anything simpler. The atoms in our language will just be letters, lowercase letters from our alphabet, things like P's and Q's and R's that you've already seen. Maybe we might use X's and Y's, and if we've run out and we need to have lots of them, we'll start putting subscripts of numbers on them. Whatever collection of formulas you might use, we just have some basket of atomic formulas, and these are going to count as formulas. And then from the atoms, we'll be able to build up more complex formulas in the following ways. If you've already got a formula, then writing the negation sign in front of it gives us a new formula. If A is a formula, so is not A. And if A and B are two formulas, then so are the result of sticking a conjunction, a disjunction, a conditional or a biconditional sign between them and wrapping the result in two brackets. And absolutely nothing else is a formula than what follows from these precise rules. This is a rigorous, formally defined language. Now, that means that some things are going to count as formulas and other things aren't. Here is an example of something that is a formula, or at least is a formula if P and Q and R are inside our stock of atomic formulas. Now here's why this thing is a formula. The first thing that you see when you look at this formula is this if-then statement right in the middle of it. This is a conditional where the first part of the conditional is not P, the second part is Q and R, and we wrapped it in these two brackets. So, if I can show that not P is a formula, and that Q and R is a formula, then this is a formula because it's a conditional. So I'll write that down there, because I use the conditional rule to make this formula out of its parts. Now, not P is a formula because it is a negation of P. And Q and R is a conjunction of Q and R. And these things are all atoms. And so what we've got here is a way of breaking this complex thing down into its components from atoms all the way back up to the complex. So P is a formula, and because it's an atom, and because its negation, not P, is a formula using the negation rule, this part here is a formula. Similarly, Q and R are atoms, so their conjunction, Q and R, is a formula, and so this consequent of the conditional is a formula, and then we wrap this in this pair of brackets and put the if-then between the two, and that shows that the result is a whole formula. This is what's called the generation tree of the whole formula. So this is an example of something which is a formula. So here are some more. P and Q implies R. This is a formula whose a conditional, whose antecedent is P and Q, and whose consequent is R. The antecedent P and Q is a conjunction, the conjunction of P and Q. So the atoms in this formula as well are P and Q and R. Here's a more complicated statement. It's not the case that, it's not the case that, P or not Q, if and only if not R. Again, it's made out of the atoms P and Q and R, but now we use disjunction, the biconditional, and negation. And notice here we've got two negation signs out the front. This is the negation of a formula. That's still a formula, and it's still a different formula than the formula without the two negations. Remember, the rule for negation said, if you've got a formula, then sticking a negation sign in front of it gives you another formula. You can apply that rule again, and again, and again, and again, and again, if you like. As many negation signs as you like. They'll be redundant, probably, but it makes a different statement. Here's another complex formula. It gives you an idea of how big and long they can get. If you look at this formula, you'll notice that it's a disjunction of a conjunction on the left and a conditional on the right, and that conjunction is a conjunction between two conditionals, and all of the conditionals are conditionals between the atoms P, Q, and R. Now, not every string made out of these symbols are formulas. For example, P not, that's not a negation because it gets the negation on the wrong side of the formula. This next example, P and Q or R, at least has things in the right order, but you'll notice that it has two connectives, the and the or, and only two brackets. And each connective, according to the rule, should bring two brackets of its own. So some brackets are missing. And here, that's missing for a reason. We really want those brackets because you could be meaning P and Q or R, which is the conjunction of P and the disjunction Q or R, or you could be meaning P and Q or R, which is the disjunction of P and Q on the one hand, or R on the other. And those two different statements mean two subtly different things. And we want to have a distinction between those two shapes. One of them is the conjunction, one of them is the disjunction. So this thing doesn't count as a formula. But the rule which made that thing not count as a formula also makes this thing not count as a formula either. This P if and only if Q then not R. Because again, this has got the two connectives, if then, and if and only if, and only two brackets. Literally speaking, this needs an extra pair of brackets outside the front. Now, as a matter of fact, in the rest of this subject, I'm going to allow you to leave these brackets out. Because they kind of are redundant, they're not doing any job. So from now on, the outermost set of brackets in a formula, we're going to allow you to leave out. I'm going to leave out because they don't really make any difference. But if you want to follow the rules literally, just imagine that they're there. So, there's some examples of formulas, and there's some examples of things which aren't formulas. For you, have a think about this. Consider a little baby language which has only got two atoms in it, P and Q. And suppose we form all the formulas out of these atoms to make our baby language. Which of these following things count as formulas in the language? Have a think about that. And after you've had to think about that, there's a harder question I want you to think about and put your answer in the discussion board. How many formulas in this baby language contain just two symbols? How about 3? How about 4? Have a think about these things, submit your answer, and come back after you're done. How did you go with that question? Have a discussion in the discussion board with other people that are thinking about the same thing. That's the end of this lesson about the connectives and formulas in our formal language. What we're going to do in the next lesson is connect up these formulas, these shapes, with the kinds of statements that you and I could make in English or another natural language. We're going to be using the formulas to find forms for propositions.